For tonight's panel discussion, The Art and Science of Water, we're really fortunate to have 4 very illustrated speakers. I'm going to let Dr. Carol Mickett introduce them in just a moment. But before I hand over the microphone to her, I wanted to just do a few brief words of welcome and a few reminders. We'll do the reminders first. If everyone could please go ahead and silence your cell phones, we'd very much appreciate it. Photography is most welcome during tonight's panel discussion, but we do ask that you refrain from using flash, so go ahead and make sure that that's turned off. If you need to get up and leave for any reason, you're very welcome to do so. The exit doors are the ones that you would have come in, and to your right-hand side as you go through those doors, you will find restrooms as well as water fountains if you need them. And then finally, we will have time for a Q&A following tonight's talk. So we ask you to stick around for that and hang on to those questions until the talk has concluded. So we'll get around to you all as well. So with that, I wanted to just mention very briefly, if Carol will let me, that tonight's panel discussion really is the brainchild of a lot of hard work and a lot of time by Dr. Carol Mickett. And I am extremely thankful to you. I'm very fortunate to have met you and to have worked with you on this project. Carol will be introducing herself, but I did want to mention that her and her work that she does with her artist and collaborator, Robert Stackhouse, who is also here this evening, is currently on view in the exhibition Skyway 2024, a contemporary collaboration, which is an exhibition that featured at 5 different art institutions within the Tampa Bay area. We were very fortunate to open first and also close last, and you still have 10 more days to see this incredible exhibition if you haven't seen it yet. This exhibition was curated here at the Ringling locally by Olaf Lusek and Christopher Jones, who are also with us tonight. So thank you so much for your incredible work on that project and really just bringing contemporary art to life here at the Ringling. We're so fortunate to have you both. And so with those words of welcome, I wanted to ask you all to please join me in welcoming Dr. Carol Mickett.
Well, welcome, and thank you for joining us this evening. I am Dr. Carol Mickett. I'm an artist, a philosopher, and a lover of science. And I'm joined by Representative Lindsay Cross, who's an environmental scientist. Al Hine, Dr. Al Hine over there, author and marine geologist, and Robert Stackhouse in the green pants, renowned international artist. We're here today to talk about art, water, science, and a lot of other things, land, atmosphere, hurricanes, ways to mitigate. Robert and I this is the installation that's in the Skyway 2024 exhibition that's in the Ringling Museum. This is an installation that is a step in a new direction for us. We've worked on water for a long time, primarily ocean and the warming of the oceans and how the warming of the ocean affects climate change and then ways to mitigate that. What's new in this installation is what's represented in the map of Florida. Namely, the only thing depicted in that is the water. And there's a lot of water in Florida. And what we were interested in and are interested in is what's the relationship between ocean and inland water? How do they react? How do they react to warming of the ocean? And how do we know what happens to climate change? Is it different what happens to the ocean, to the inland water? We're going to talk about all of that. And interspersed in that discussion will be art. Because we have learned and known for a long time that art is a conduit into science. People find that they can engage in art and they can see the principles of science in it, and then they can go and look further into scientific inquiry. So art and scientists are good friends. So let's get started. According to scientists, Early Earth was likely covered almost entirely by water, essentially a water world with no visible continents, suggesting that the planet was initially covered with a global ocean, particularly around 3 to 4 billion years ago. So this is a contemporary rendering of what that may look like. And one thing that's interesting, when I was looking for an image of this, I thought I was just going to find a blue sphere. But what's there are clouds, because if you're going to have water, you're going to have an evaporation cycle, and you're going to have clouds. And it's claimed by scientists that at this early time, it was endless water, rain coming down. So, Al, do you want to tell us more about this?
Can you hear me okay? Well, I'm a geoscientist, so I think in different timescales. It'll take you back about 4.6 billion years, and we'll just talk about 100 million years here or there. Pretty soon you're talking about real time. But the Earth formed about 4.6 billion, Earth and the solar system formed about 4.6 billion years ago from a cloud of charged particles that eventually formed the sun. The sun ignited through fusion, and the rocky planets formed as a result of many, many collisions of small rocks that impacted with larger rocks. And after a few hundred million years, the Earth became the size that it is basically is today. And through all those collisions, an enormous amount of heat generated, and the Earth was fundamentally a molten ball. And close to the end of that, it's called the impact of the bombardment period, the Hadean, which is an appropriate period of geologic time. It's a Hadean eon. It's the first 500 million years of Earth history. A very large object, towards the end of that bombardment phase, a very large object, almost the size of Mars, impacted the Earth, and an enormous amount of material from this molten Earth was cast off into space, and that created the Moon. So the Moon and the Earth were formed almost at the same time, but the Moon is a piece of the Earth, and the astronauts that went to the Moon and brought back rocks have shown that they are similar to the Earth. So the Earth started to cool, and I want to point out one thing. The Moon is incredibly important as far as the Earth is concerned. We're unusual in the fact that we're a small planet with a large moon. There are huge planets with much smaller moons, but the Moon provides a gravitational stabilization that controls our rotation. So we have predictable seasons, we have predictable years, otherwise we'd be rotating all over the place without this gravitational lock between these two bodies. Anyway, so as the Earth started to cool, the Earth's crust started to form, and of course there's an awful lot of degassing. If you look at modern volcanoes today, there's a lot of gas that comes out of volcanoes along with volcanic ash and volcanic bombs and rocks that are tossed out of the volcanoes. But there's an enormous amount of gas, and part of that is water vapor, and part of it is CO2, and part of it is H2S. So there's a whole chemistry of gas that goes into the atmosphere, including water. And so as this cooling formed and the Earth's crust was solidifying, water formed and the atmosphere formed. So the atmosphere and the Earth formed together approximately the same time by about 4.1 billion years. The two were formed, and we'll get to the continents later on, but basically for a short period of time, maybe 100 million years, 50 million years, something like that. Nobody knows for sure because we don't have rocks that go back that far in time. They've been recycled by the Earth so much. But starting out, the Earth basically was a water atmospheric planet.
Cool.
And here it is, right there.
So, Art, Carol and I, about 20, 30 years ago, decided to work with water as kind of a theme of our collaboration. And one of the things we set out to do was find different ways of depicting water and how it affected us and how we affected it. So it's multi-layered. Water is kind of difficult to pin down in a way, and it goes where it wants to go, and then it evaporates, changes shape. And this particular painting, taken in context with the photograph of the water world that we just saw, is really quite revealing. When we painted this painting together, we were thinking of the dynamics of water, the fluidity of water and the motion of it. You can see this painting. It's here at the Ringling. It's part of the State of Water, and it represents, in this case, the Atlantic Ocean. But it's called Mickett. So it's, you know, it's not a picture of water, it's a memory of water. It's something that exists with us. So this painting is very important in its layered effect, and as things change, its context, it changes its deep meaning. So we wanted to pursue depicting water two-dimensionally as well as three-dimensionally, and this is in the blue, and it was done as a four-part sculpture that went in a circle. You walked through room to room, and it was like being immersed in the water. In this case, the water is kind of all riled up, and it just created a sense of being immersed into the water. And, you know, and somebody, a fellow artist, you might be familiar with this guy, William Turner. The thing about this painting is that even though it was done in the 1860s, the Industrial Revolution was starting, and there's a sense of Turner depicting what, you know, the consequences of the Industrial Revolution upon nature. And this is really an interesting painting in that it sort of sets up what we are seeing in this talk, is that you have ocean, you have clouds, and you have snow. And so you have all that cycle going on in this particular painting, as well as you're being immersed into the painting like it was in the blue.
If the Earth was completely covered in ocean, how did we get rivers, lakes, streams, ponds, and so on?
Okay, that's me. The one thing I just want to quickly mention is that in the scientific community, there's been some discussion about where water came from, and a number of people think, and still think, that much of the water on the Earth came from comets, extraterrestrial features, and that still exists, and probably some water that exists on Earth did come from comets. But the chemistry of the water now, the geochemistry of the water, present-day water, tells us that it mostly came from basically the cooling of rocks and the degassing of rocks. As the Earth's crust became formed, the center of the Earth, of course, was molten, and it still is molten. The core of the Earth, the outer core of the Earth is liquid, the inner core of the Earth is solid, and of course it rotates, and that creates the Earth's magnetic field, which is really important to protecting life from radiation from the sun. So we're kind of living in a magic world, or a Goldilocks world. Earth formed just far enough away from the sun such that water can be a liquid, or that H2O can be a liquid. If we're too close, it would burn off, it would evaporate. If we're too far away, it would freeze. And so we're kind of in a Goldilocks, 92 million miles from the sun, that allows H2O to survive both as water, gas, and as solid. As the crust of the Earth cooled, or as the Earth started to cool, heat escaped and allowed the crust to start to move and break up. And this is called plate tectonics. And when I was in college, we were never taught. I graduated in 1967, that kind of tells you about where I come from. And so I saw a real paradigm shift in how humans looked at the Earth, or how we learned about the science of how the Earth behaved. So we learned about plate tectonics in the early 60s, and now it's an accepted theory. We don't fully understand how it works, but there's no other competing theory out there that's just as believable. So we have what's called plate tectonics, where pieces of the crust of the Earth move around, driven by the interior heat of the Earth escaping from the Earth. And so pieces of the crust of the Earth bump into each other, move back and forth, and as a result, some of that crustal material is subducted, remelted, and then comes back to the surface of the Earth in lighter and less dense type of rock that's rich in aluminum, silicon, sodium, and potassium, whereas the ocean basins are rich in magnesium and iron. They're heavier rocks. So the crust of the Earth become differentiated between continents and ocean basins. You can think of a continent as a kind of a bar of ivory silk floating in water. It's lighter, it's about 30 kilometers thick, where ocean crust is about 5 kilometers thick. So we created the continents. The continents were created early on, probably soon after the Earth was formed, but for a period of time it was an ocean Earth, and then the continents formed, and that completed the hydrologic cycle. So we have an ocean, we have clouds, we have evaporation. Moist air can reach the continents. When moist air reaches the continents, it cools. It can get updrafted through thunderstorms. What we have here in Florida, where the air is lifted up, it cools, it becomes oversaturated, and it rains. Or wind can blow air up against the mountains, it rises, it becomes supersaturated water, it snows and forms ice and glaciers. Or it can, warm, moist air can meet cold air, and we have frontal systems that pass across the United States, and we just had a front pass through the other day. And so we have warm, moist air meeting cold, dry air, it rains. So that creates the hydrologic cycle. Water is evaporated from the ocean, reaches the continents, it cools, it falls in the form of rain or snow and ice. I'm going to stand up here without, see if I can kill myself falling off the stage.
Give you a pointer.
Yeah. These are pictures going back in time, geologic time. So here the continents have formed, and since about, since continents first started to form, 3.8 billion, 4 billion years ago, something like that, we've had 5 major continents form, break up, form, break up, form, break up. And the last one was a megacontinent called Pangaea. There's a continent called Gondwana here, this is Laurentia here, these large masses. You can see North America, you can see Scandinavia, here's Greenland, here's Africa, here's South America, and here's Florida. Florida actually was a piece, not part of North America, so it's an exotic terrain, so to speak. And so I cover that in my book on the geologic history of Florida. Well, as a result of plate tectonics, these large masses form together, and when they collide, they create mountain ranges. So the initial cratons, the initial bars of soap, ivory soap, actually got larger and larger as they banged into each other and created mountain ranges. So the Appalachians made North America larger because of this type of collision. So as a result of this collision, we have a huge mountain range that extends all the way down through here. The Appalachians are here, the Mauritanian mountains are here. So this was one large continental mass that existed for about 50 million years, but the problem is it acts like a gigantic blanket. So the Earth is constantly exuding heat. So it acted like a blanket, and as a result of these large continents coming together and forming one large piece, they break up quickly. They break up quickly because of the fact that they just trap heat beneath them, and as a result, the seafloor spreading. And so the next picture, here we go. Here they're parting away, and you can see Florida has now joined North America, which is kind of cool. So the basement rocks of Florida are actually pieces of South America and Africa. So that's another story that's kind of unrelated to what we're talking about today. But this is the formation of the North Atlantic, the Gulf of Mexico, and the Caribbean, enormously complicated tectonically. And then later on, the South Atlantic Ocean formed, and this ocean formed here. And of course, we can look at a modern map today and see how wide the Atlantic Ocean is. But this is what the Earth looked like some time back. And this is just a diagram that I put together about the Florida platform. I consider, or geologists consider the Florida platform, Florida to be a platform. And the state of Florida is just a piece of a larger platform. That half the platform was flooded with water. We've had multiple sea level fluctuations in the past. The Florida platform was completely exposed. There were shorelines way out here at one point in time when we had glaciations. And now the shoreline has migrated to here. The shoreline is a very ephemeral feature. It migrates back and forth. And at periods of time, Florida has been completely underwater. Matter of fact, most of its geologic life, Florida has been submerged. And it's only now, it's an unusual period of time where we actually have dry land at which we can occupy. And this just gives you some of the sense of the bathymetry around Florida, the Gulf of Mexico, the wide shelf here. This is the Florida platform. And at one point in time, the Florida platform and the Bahamas were all one contiguous large limestone platform. So that's another part of the story locally here that's important, is that this is a huge area of limestone accumulation. Florida is different than most of the rest of the states in the U.S. in the fact that it is composed of limestone situated on early basement rocks, which were once South America and Africa.
This particular painting, I think, fits in that what we discussed earlier. Is the context changes a little bit. I'm looking at this painting, which was done pretty much to illustrate the topography of the below the water line in the Gulf of Mexico. It continued our different ways of depicting water. In this case, we depicted the structure that holds the water, and we were very interested in the linear quality of the topographical lines. Taken, by the way, from a map that was all about locating where oil is. The University of South Florida, the professor gave us the map to do that. So the serpent is kind of sneaking in a little bit more of what we're going to be talking about is traditionally in mythology and stuff, serpents have quite often been boundaries or protective things. And in this case, the serpent sort of acting as the boundary of the land So we're going from ocean to land on this image. This is my new interpretation of it.
Okay.
Why is ocean salty and inland waters for the most part not?
The ocean, one of the things about water is that it has electrical properties in which it can easily dissolve rocks. And as the water evaporates from the ocean, it's carried to land and lands on land, it falls on land. It goes to the atmosphere, and there is CO2 in the atmosphere. There's always been CO2 in the atmosphere. There's always been sulfur in the atmosphere. There's H2S. And so the water can dissolve the CO2 to form carbonic acid. It can dissolve the H2S to form sulfuric acid. So when rainwater strikes the land, it's already slightly acidic. It's not pure H2O. Plus there are many other things in the atmosphere that are dissolved in the rainwater. So it's not distilled water. It's not pure H2O. It actually has a chemistry to it. And because of the acidity and the chemical properties of water, it's capable of dissolving rocks. It's capable of dissolving rocks whether or not they're hard as diamonds or if they're soft as a soft limestone. And so over periods of time, when water runs off the continents, it dissolves rocks, and large mountain ranges can actually be reduced to much smaller features. So as it dissolves rocks, it carries what's in the rocks, either as sedimentary material like muddy rivers flowing into the Mississippi, flowing into the Gulf of Mexico. There's a lot of suspended sediment and mud, but there's also a dissolved load as well. So all this chemistry is coming into the ocean. This is from dissolved rocks on land. Now all this chemistry enters the ocean, and it's used by the ocean. We have phytoplankton, we have plants and animals at the base of the food chain and then further up the food chain. So much of the sodium, much of the potassium, much of the calcium, much of the sulfur, much of the iron that comes from the land is actually consumed by the biota in the ocean. The ocean is very effective in using a lot of these nutrients, and we need it in our own body. We're not just water. We're not just carbon, hydrogen, and oxygen. We need iron. We need various things. We need potassium. We need potassium, from what I understand, is essential to the DNA, holding the DNA molecule that defines our bodies, that sort of thing. So the ocean is alive with life and consumes a lot of this chemistry, except for sodium, except for chlorine. So sodium and chlorine kind of get left alone. And so they accumulate in the ocean, so the ocean becomes salty. But there are other things, there are other salts as well, but sodium and chlorine seem to be the dominant component of the ocean. Now, when water evaporates, the sodium and the chlorine aren't evaporated. H2O is primarily evaporated, so it's left in the ocean. So basically, that's how the oceans got salty. Now, there are lakes that are salty too. Great Salt Lake, the Dead Sea, for instance. And so groundwaters and surface waters that flow to interior basins that never make it to the ocean can dry up, they evaporate, and what chemistry was in that water precipitates out and creates NaCl, it creates calcium sulfide, it creates lithium carbonate. That's where we're getting lithium now for batteries. We're looking at salt deposits in the Salton Sea and other places like that. So but basically the ocean is salty because of the fact that so much has run off from the continents, accumulates in the ocean. Most of it is used by the biology of the ocean or sinks to the ocean floor, it's consumed or is deposited in the ocean sediments, but it leaves behind the sodium and the chlorine.
Right.
Yeah, I forgot to talk about that, but that's basically what that says.
So let's move to inland.
Okay, Albert Bierstadt, Valley of the Yosemite, and in the previous map you saw a map of the inland ocean, and this is part of that inland ocean. And it's interesting how in the late or mid 19th century the artists went into the wilderness and recorded what they could see and report back to us, since we couldn't. As when we lived back then, people weren't able to travel to that area extensively. But this is a beautiful example of kind of an ideal thing. I mean, the water is clear, the mountains are strong and high from tectonic rise and stuff like that, and it's just an idea of what the dynamics of these continents clashing into each other, and what this land that we have is made out of. it just shows how the art records this kind of stuff. It brings a visualization to a lot of science.
And one thing that happened when Bierstadt and other artists at this time, there would be, when they displayed their work, there would be lines of hundreds and hundreds of people that would line up to see this, because this was the only record of this that people got to see, because they didn't travel there. There weren't photographs. So in this case, the artists were the conduit to find out what our country was like, but also to start seeing this dynamic, which questions and brings in science. What's the history of the world? How did this come about? I mean, it is so dynamic.
Okay, I guess that's me again. One point I'd like to follow on what this Carol said, and I should have mentioned it in my last comment, was that water enormously is capable of enormously shaping the land surface. Much more so, perhaps, than many of you might think, and certainly what I thought back when I was much younger. I mean, what do you think of the Grand Canyon? The Grand Canyon is a water-created feature. It's absolutely enormous. There are many canyons around the surface of the earth. There are glacial canyons, there are fjords. These are all carved by water or ice, that sort of thing. But one of the things that really amazes me is looking at mountain ranges. The Himalayas are about 9,000 meters, 8,800 meters high, I think is about the height of Mount Everest. And it's still rising as a result of India being tectonically colliding with South Asia. So the Himalayas and the Himalaya-Tibetan Plateau are still rising as a result. You look at the Appalachians, and these mountains are modern mountains. They're happening today. They started about 45 million years ago, and the Himalayas are still rising today. As a matter of fact, they've got instruments on Mount Everest to show that it's rising about 4 millimeters per year. That's not much, but given 50 million years, that adds up to some serious distance. The Appalachians are 300 million years old, as indicated by a couple of slides ago. Many of my colleagues think that the Appalachians are as high as the Alps, or as high as the Himalayas. The Himalayas are almost 9,000 meters. The Appalachian Mountains are 2,000 meters. That's 7,000 meters of rock. Where did 7,000 meters of rock go? It was basically eroded by water, essentially. And during high latitudes, when water freezes, it expands, so it gets into cracks, it breaks it up. That's called physical weathering. In lower latitudes, where it's warmer, there's chemical weathering, so the rocks are eroded. So you can go up into North Carolina or places in the southeast of the United States and look at something that looks like a hard rock and actually reach in and grab a handful of it. The rock has been basically dissolved or it's softened as a result of chemical weathering. So because of physical weathering and chemical weathering over the years, over hundreds of millions of years, we can drastically shape the topography of the continent. So that's the key point. Now this slide is kind of a small subset to that. It's a little bit complicated, but basically I wanted to show, let's look at scales. When you always look at a chart like this, it's important to look at the scale. That's 10 meters and this is 10 kilometers here. So we have the ocean here and you have limestone, which is now in Florida. So this is limestone. And we have mixing zones, various mixing zones. When you mix fresh water with salt water, it creates a slightly undersaturated solution, slightly acidic solution, so you can dissolve rock. And that's chemistry that I don't have time to explain. But nevertheless, when we have marine phreatic and vadose, these are, like I said, it's a complicated term, slide into terms there that I don't need to define. Vadose means it's solid water. Vadose means that there's air with the water. Particles with the water. But the point is that we have a mixing zone here of salt water and fresh water that's coming down from this, creating this mixing zone. And where you have this mixing zone, you have this increased salinity, this increased capability of dissolving rocks, and you can create caves. So that's the reason why Florida is loaded with caves as a result of this mixing, partially because of this mixing between salt water and fresh water. This is actually called the Cahout Convention. Cahout was a famous geologist who lived back in the 60s, and he came up with this idea. So we have salt water that's way down, and that can be mixed with fresh water that's further up, and where the two mix can create caves. And so ultimately those caves can collapse and create sinkholes, which is a slide coming up that shows that later on. But this is important to show that water has a very effective capability of not only lowering the topography or changing the topography, but dissolving the rocks that are beneath the surface of the earth. Well, yes, and this just shows the Florida aquifer. So limestones are porous, permeable, and they can be impermeable as well, depending upon lots of different things. We have what's called the Florida aquifer, which is a part of the stratigraphy that lies beneath our feet. It's very permeable, so water can flow through it. And it gets recharged from up here, actually in the southeastern part of the United States. The numbers here shows the thickness of the Florida aquifer. It's 1,000 meters, 600 meters, and this goes to 0 here. So the limestone basically ends in South Georgia, South Carolina, and then Alabama. And it's topographically higher up here, so water that can enter the Florida aquifer here and can flow downhill like this has what's called a hydraulic head. And so if there's impermeable rock on top of the porous rock, there's a hydraulic head, and if we can create a crack which can dissolve out, that gravitational force can force that water up through that crack and create a spring. So that's why we have springs in Florida, because they have a hydraulic head where the water has been charged, enters the Florida aquifer north up here as a result. So Florida is an area where we have an amazing number of these large springs, but also billions, literally billions of tiny springs as small as your finger or as small as this handheld thing that I'm holding right here. The big ones are the famous one, that's where the manatees go, and that's where we like to dive and canoe and kayak and do that sort of thing. But actually where the Florida aquifer reaches the surface, there are many, many smaller springs in which fresh water can reach the surface as a result of this hydraulic head that's built up by the recharge area in this part of the world.
Wow. Wow.
And this is part of the aquifer, this porous rock through which the water flows.
Right, if we could take a big knife and cut Florida in half, we'd look at it, it would look like Swiss cheese. It's just full of holes. And water can flow through those holes, but not through all of it. Like I say, there are parts that are impermeable. So we have a permeable section, an impermeable section, a permeable section, an impermeable section. And a groundwater geologist, I'm not a groundwater geologist, I'm a geological oceanographer, but I know a little bit about it, not to be somewhat dangerous. That if you can drill down into this, you can find an aquifer where you can withdraw water, or you can find a deeper aquifer in which you can put sewage or waste. And so that's a huge issue right now. I don't quite fully understand exactly how it works because it's not my thing, not what I study. But aquifer recharge, where we can actually store water, take water in dry areas, and we can take it and pump it down rather than having a superficial reservoir. We can actually put it into the aquifer, and hopefully it stays there and doesn't get mixed with pollutants that we actually put down deeper. And we can withdraw it later on. So it's called aquifer storage recharge, ASR. And that's something you read in the newspaper about. There's an option of whether or not the groundwater geologists that are in the various water management districts in the state are capable or should take water from the surface and recharge to the aquifer and withdraw it later on.
Okay, Lindsay?
Sure, I'll just add, Dr. Hine, I'm learning so much from you, so this is excellent. One other thing that's so unique about Florida is the limestone and the geology that we have, and it contributes to the springs and the sinkholes that we have. We have more than 300 springs in the state of Florida. Many of those are first magnitudes or larger springs, and of course, things like Blue Springs, Manatee Springs that many of us go to recreate. And because of those porous features with the limestone, water that falls onto the ground in rainfall or discharge moves very quickly through that porous limestone. And so if you've heard anything about pollution that we have in our springs, those are areas that are not acclimated to having a lot of nutrients, to having a lot of nitrogen or phosphorus. And those are both components of fertilizer, but also waste from humans and animals. Those areas were developed with very low nutrient inputs. And so you start to see more pollution from sewage, from septic systems, or from fertilizer, particularly in the spring shed areas in northern parts of the state. You can see degradation in those systems very quickly. And you can start to see a shift from some of the rooted vegetation, so what we call submerged aquatic vegetation, to more floating algae. So you're decreasing the light availability for the grasses that are rooted in the sediments, which are food sources for our manatees. You start to see a change and a degradation within that whole community. So instead of having that rooted grasses, either freshwater or in our coastal areas, salt-tolerant grasses, you're getting rid of that food sources and you're starting to see more of that floating algae, which is not something that the manatees and other animals are eating. But because of this porous limestone, when you have pollution, septic systems, or if you're applying treated wastewater, in a matter of hours, you can detect that into our spring systems. So through the work of mapping caves, with scuba divers and with geologists are actually able to see if you apply polluted water in one part of an area near Tallahassee, in a matter of hours, they can find it in different areas like Wakulla Springs.
But I want you to see the giant sinkhole, which of course all of us worry about. That will that occur in my yard? Will that occur in our city? And we certainly don't hope we have one this size. And this is a quick look at how sinkholes are made, but I'm going to skip that because of our time constraint.
Okay, back to art, and Monet's water lilies is always fascinating me because I always thought, well, Monet's water lilies, it's a painting of water lilies, but then I started really looking at it, and there's not very many water lilies there. What you're really looking at, you're looking down at the water, which reflects what's up above. So what you're really seeing is water and clouds. And when you think of Monet and you think of the latter part of the 19th century, the early 20th century, how science was really very much part of what the Impressionists and Expressionists were dealing with in how it taught them about the color spectrum and all other kinds of things, which really revolutionized the way artists saw the world and how, since we saw the world. So I've always thought that this was a very important painting in that not only there's no horizon in this painting either, so you're really looking down at the ground to see what's up above you. So it's a really total immersive kind of thing. It's fascinating.
Right, in that.
So here's more inland water. So this is a 5-part mosaic that Robert and I did. It's in Richmond, Virginia. And it's a depiction of the whitewater of the James River. And why this is important is that inland water, so the river came up from the Atlantic Ocean, and the ships would come up this river, and what they encountered was this, the fault line, the whitewater, and the ships couldn't go any further. So what happened was people offloaded the ships, and Richmond was created. This has happened all over the world. So water comes, of course, sometimes it's calm, but oftentimes it's robustly moving and filled with rocks and fault lines and falls. And what happens is rivers have always been a way to traverse inland, but they also have been so important in us forming communities and places to live. And without this river and the way it was at Richmond, Richmond would never be there. It would have just gone on and on into the west. So you can see how turbulent this fresh water is. So it's not just ocean that can be turbulent, and inland water can be turbulent as well. Okay, carbon dioxide and methane and related challenges. Lindsay, do you want to talk about this?
Okay. Well, I think all of us recognize this picture as the Deepwater Horizon oil spill, and I believe we're close to the 15-year anniversary of that. Is it more than that? I think it's around that. Anniversary of this spill. I believe just less than 10 individuals died on this explosion on this oil rig, as well as having immeasurable impacts to the Gulf of Mexico, to the ecosystem. It's important that we look at this because many of the things that we're doing as humans, particularly the burning of fossil fuels, in a very short time are changing some of the fundamental things about our atmosphere and about our Earth. when you hear Dr. Hine talk about 4+ billion years, many of the things that we're doing have been practices over the past centuries. But in a very short time, through the burning of fossil fuels, which contributes carbon dioxide, other oxides, methane, is changing the configuration of the atmosphere, causing the warming and a lot of the impacts that we're seeing here, whether it's the hurricanes we experienced this year or the acceleration of forest fires that we're seeing out in California.
Yeah.
And we all know that as humans, we produce a lot of waste. Most of us, if you had any impacts from hurricanes Helene or Milton or Debbie, you probably are more intimately familiar with the amount of things that we have, the amount of stuff that we have, and the challenge of what we do with that waste. The debris that was accumulated during those storms is an ongoing issue. I know in many of our communities, there's still storm-related debris in our front yards, in debris staging sites, and communities south of us are still continuing the process of cleaning up from Ian several years ago. But during the in landfills, while this material decomposes, it also emits methane into the atmosphere. And so do these guys right here. We know that cows are a source of that as well. And there are efforts by scientists and people who are working in the agricultural community. Archibald Biological Station in South Florida in the Lake Wales area is looking at some experiments of actually how to capture some of the methane gas that we're seeing from on our cattle farms. There's also a term called renewable natural gas, which is capturing some of the methane from landfills and trying to use this as a supplemental source. Some people in the environmental community kind of bristle at that term renewable because it is it's still not a clean source of energy, but it can be included in some of the mix of the energy sources that we're using.
It also is the case that in Australia, they have found that using red algae, if they feed that to the cattle, stops the methane. And even Australia has made it a requirement that the cattle ranchers use that. And I know that that's been done research in this country about using that, but there's some question about the invasiveness of the red algae. But the other thing that we also know about cattle is that it's been argued recently that if we look at all of the pasture land that has been created, and it's been created by taking all the trees away, deforestation, and that the land that's left, that pasture land, does not absorb CO2 anymore because it's just barren. So one of the arguments is if we got rid of all of the pasture land and reforest the world and went to a plant-based diet, there would be no issue about climate change.
That's probably not going to happen.
Yes. Well, there's practical things and there's theoretical things.
A hurricane. This is something that we know intimately here in the state of Florida. We know that we're seeing stronger, more intense hurricanes. Maybe not increases in the frequency, but certainly increases in the severity of the storms, with the most recent ones, Helene and Milton. In the past 7 years, there have been 6 major hurricanes that have hit our state, and so numerous federally declared natural disasters that take many years to recover from.
And we know that the warming of the ocean makes the hurricanes intensify. Actually, it was that started Robert and I on the path of looking at water and ocean. And we've done projects where we have done an ice cube project where we say, well, if you want to cool the water, put an ice cube in it. So we've done a whole project about, and we've done it on research vessels across the Pacific and the Atlantic, putting saltwater ice cubes into the water.
What's also changed is that the western Gulf of Mexico and the Western Caribbean are heating up faster than they've had in the past. And as a result, hurricanes can form very quickly just offshore. And a low pressure system can go from a subtropical storm to a Category 5 storm in 24 hours, which is remarkable. 39-mile-an-hour winds to 155-mile-an-hour winds within 24 hours. And it's just 100 miles offshore and come onshore. So the days where we can watch a low pressure system leaving the west coast of Africa, tracking across the ocean, we have 5 days, we have 4 days, we have 3 days, we have 2 days to prepare for it. We might have 24 hours to prepare for a Category 5 storm, which is really what worries me, is that we have not really seen a significant hurricane, in spite of the hurricanes that we've had in the past, particularly Ian a couple of years ago. If we had a Category 5 hurricane pass over the Tampa Bay area, it would be truly catastrophic. And these storms now can form just offshore and be here before we know it, before we can fully prepare.
Dr. Hine, one of your colleagues, Dr. Gary Mitchum at the University of South Florida, is doing a lot of work on sea level rise and the changes that we're seeing in the climate. With the hurricanes, when we have warmer waters and warmer ocean waters, that warmer air can actually hold more moisture. And so that's one of the reasons it's contributing to higher rainfalls. If you think about some of the summer storms, not associated with a hurricane or a named storm, but just an afternoon storm that can bring a foot of rain in a matter of several hours, or the storms, the major hurricanes that are bringing 18, 20 or more inches of rainfall in a short period of time. It's because that air actually is more saturated than it has been in the past. And so the intensity of the wind speed is increasing, but also the ability to bring more precipitation in a very short period of time.
And I'm sure many of you have experienced this. I know Robert and I live in Tarpon Springs, and in Tarpon Springs, when it rains or we get high tides, it floods our streets. And I'm sure in many places that you live in, you see similar things.
So as a legislator, I'm serving in my second term in the Florida State House. My first term, it was right after Hurricane Ian impacted just south of you, primarily Lee County and Fort Myers area. In response to that, what I'm seeing in my own community, which was impacted in Pinellas County by Helene and Milton, is there's always an urgency to rebuild, to get back to where you were, to get people back to work, get businesses open, schools, allow people to rebuild their homes. But what I've seen in just a short time in the legislature is that sometimes that urgency to rebuild is putting us in more precarious positions. There are desires to rebuild in the same places that we've built, to allow for bigger developments in the same locations. And in particular, there was a bill last year that I strongly opposed that would really tie the hands of local governments. If there was an older structure that had any defects to it and didn't meet codes or conditions for any particular reason, it could be that maybe it was not ADA compliant, or there was some minor thing that needed to be updated. A developer would have the ability to essentially have that building condemned, have it demolished, and then put a new structure as tall and as large as something in the similar situated zone. So that means in our beach communities, the areas that are most vulnerable to our storms and our hurricanes, if you had a small 2-story motel, but it was right next to a 40-story apartment or complex, there's nothing that those local governments can now do to prevent something that's taller, that has more people that need to be evacuated for being developed into that area. And so as we see sea level rise, as we see the continued threat, particularly to our coastal and our floodplain areas, we need to be very careful that we're in a rush to get back to normal or to allow more people to come back into that area, that we're not setting ourselves up for more catastrophe in the future.
Well, this is, I took that picture back in the 90s when coastal zone management was basically non-existent. You could build just about anywhere. And that picture showed a condo built at high tide line. And the high tide was no beach, and now there's no beach in front of that condo right now. This is what a barrier island looks like in its natural state. But this is not too far south of here. The sea level continues to rise. Sea level is continuing to rise. And particularly with stronger storms, the barrier islands without human presence normally look like this. This is a natural barrier island. So what we're trying to do is prevent this from happening, which is really difficult. And we'll reach a point where we can no longer build seawalls, we can no longer afford beach renourishment, and eventually will have to lead to managed retreat. And I use the term ultimate abandonment, which I know is politically incorrect, but that's eventually where we're headed in the multiple decades coming.
Something that we also see during storms, but also regular occurrences, is failures of our infrastructure. Many of our wastewater treatment plants and the pipes and the pumps that support that were built in the 50s or earlier. I know that my home is over a century old, and some of the original pipes were made out of cardboard. It's called Orangeburg. And so you can imagine that 100 years of a cardboard under the soil is not going to last very long. So we are seeing that we're having wastewater spills, particularly during heavy rainfall events, and a fundamental need for us to upgrade infrastructure. Something that I had proposed, a bill that I sponsored last year and will bring back this year, would start to look at how we can best prioritize the money that we provide from the state to our local municipalities for upgrading infrastructure, by being able to identify some of the bad actors, places where we're having chronic spills, looking at vulnerability to things like sea level rise, or whether they're in coastal high hazard areas, and if there's impairments, if the water bodies that discharge is discharged into, if those areas are polluted and we're starting to see degradations in the ecosystems, those type of plants need to be raised up to the top of the list, and make sure that we're making those upgrades there and doing things, protective measures, so that they're not vulnerable to large wastewater spills during our storms.
This painting is in the Ringling collection here, and I don't think it's up on the walls anywhere, but anyway, it's an interesting painting in the context of what we're talking about. In the 1780s, early 1790s, it's a picture of a harbor. We've seen hundreds and hundreds of these kind of things, but there's a lot of stuff on the shore right there, and you get the feeling that these artists who are dealing with the growth of maritime travel and maritime destinations and how picturesque they were depicting, maybe unintentionally, but depicting sort of what we're talking about right now, is the degradation of the landscape. And so it's kind of an unintended consequence of this particular artist, who was painting a wonderful harbor scene. But this artist knew what he was doing. This is Turner again, and it's just an example of sort of the unintended consequences again of the Industrial Revolution happening in England and Wales. It's a watercolor painting. It's just really beautiful, I think, because it's so Turner-esque, and yet it's horrible. There's that smokestack spewing that black stuff coming out, and he got in a lot of criticism for doing that. He was very aware of this. We're aware of this too. This is part of the piece we did of the water is really basically getting too hot. It looks like it could be event horizon, but it was done with really just emphasizing the fact that the water really is getting too hot.
So natural ways to mitigate this. Well, one is trees. Trees are incredibly important in different ways. Trees, large trees down to mangroves to grass. They both help to absorb CO2, they help to keep the land in place, they create shade.
One of the other values of these natural systems, such as mangroves and these upland forests, is they have the ability to store carbon in their root biomass and in the soils. So there is a natural mitigation process that's happening in these systems, both on the land and in the water. We know that seagrasses and mangroves, even things like oysters and clams, can absorb some of the carbon dioxide that gets into our oceans, and it's a natural way to mitigate for some of the carbon dioxide emissions through the burning of fossil fuels. One thing that I'm proposing through a bill is that we do an assessment as a state of these type of ecosystems, both our natural areas as well as our agricultural and aquaculture, to understand their ability to store carbon, how we can maximize that efficiency through preservation, through different management, improved management of things like timber plantations, so that it's another way to incentivize the preservation of agriculture, preservation of natural systems, and help to support some of that climate mitigation. A really exciting kind of strategy for conservation that we've seen in the state is something called the Florida Wildlife Corridor. And this is an idea that was born out of a local photographer named Carlton Ward Jr. from the Tampa area. He's now a National Geographic photographer, and you may have seen his work through his videos and documentaries. But working, and the next slide, we'll see kind of the inspiration for this. Back to that area called Archibald Biological Station, down in the Lake Wales Ridge area, there's a bear biologist that had tracked a bear, who wanted to see the pattern of this bear, and noticed that over about a month period, this bear walked over 100 miles. Went down from the Lake Wales Ridge area, went up towards Orlando, didn't make it across I-4, of course, but kind of circled its way back there. And so it got him and others thinking about just the natural migration patterns of some of these large animals like the Florida black bear and the Florida panther. So kind of the idea of this Florida Wildlife Corridor, if you were a panther or a black bear, are there ways that you could still move through the state of Florida safely without being hit by a car or kind of running into a dead end? And so this is a depiction of something that is now in state, has been adopted statewide as the Florida Wildlife Corridor. It's about 18 million acres across our state. It starts at the base of the Florida Everglades, and it goes all the way up to the Georgia and the Alabama border. More than half of this land is protected, but there are still significant areas that need to be protected. Many of those are agricultural areas like cattle, and timber. So as much as we want to get rid of those stinky cows, those agricultural areas are providing a connection point between some of the larger protected areas that we know of, like the Everglades or Ocala or Osceola National Forest.
The other thing that's important about the corridor is it preserves the trees. So you can't get rid of these trees. And as Lindsay said, the trees are big absorbers of CO2. The other thing trees do is they create shade. They're big things that cool our planet and help to cool the ocean. So they are things that really save us, as do the mangroves. So mangroves absorb CO2. They're one of the biggest absorbers of CO2. And if you had a forest of mangroves, it would absorb more CO2 than a rainforest. Now, the thing about plants is that they have photosynthesis. So they absorb CO2, they use the carbon, they store the carbon, but they give off oxygen. So they help us because we need oxygen to breathe, and so does the planet to live. So they are really one of the most amazing things. And this is a painting of Robert and mine called 3 Carbon Catchers. And of course, they're mangroves.
Well, we painted them like they were icons. They're that important to us. And so this is the green swamp. Swamps are also great carbon sinks, or I like to say carbon traps, and as well as other things. But just another watercolor of the live oak with its shade and all the things that it can do. Now this is an interesting thing that when we were exploring the dynamics of the Gulf of Mexico, is that there's 1,000 sperm whales that live permanently in the Gulf of Mexico. And during the event horizon is when I first found out about it. I heard about the community of sperm whales that were really being agitated by the spill, and it was in their particular area where they are deep divers, and they were exposed to this and tried to stay out of the way. But the thing that I found out, and Carol and I explored it more and more, was that there's a thing called the whale pump. I mean, this is a term, and this is what these whales are doing. They of course, you see them on the surface a lot, and what they do is they feed off of photoplankton as well as zooplankton, which is what this picture illustrates. But what they do is they eat some of this, and they go down looking for more food. They go down to the bottom of the ocean, and they feeding down there. But then they have to, what all animals do is they have to defecate. So they come back up to the surface, and they defecate on the surface where all this photoplankton is. And what they do is they fertilize the plankton, the photoplankton especially. So this photoplankton then is absorbing CO2 as well. So they're actually creating more photoplankton. They're helping to grow the photoplankton. And then what happens is when the photoplankton dies, it falls down into the bottom of the ocean and gets locked into the ocean like other things can do. So we found out that whales don't just sort of lumber around making songs for us to enjoy. They're actually very involved in mitigating the control of the climate. And I've heard it said, and Phil, I think, told me this, I believe, that this activity is responsible for a good 50% of the oxygen in the world. So this study came about when they were trying to defend they were dealing with not killing whales. They were saying it's not good to kill whales, and because they're doing much, much more for us.
So this is just one of the systems where different entities work together. So the whales have the photoplankton, as Robert said. The photoplanktons absorb CO2. When they die, they sequester the CO2 down in the ocean and give off the oxygen. I mean, it's just a beautiful system. And so save the whales, yes, takes on a whole different meaning.
I just want to add one more thing. We attended a talk at USF actually about mitigating the CO2 in the oceans, and it was there was this one slide where it showed this machine that was floating in the water like an island that was going to capture the CO2, and they had a couple of whales floating around underneath it, and I think they were just there for illustration. I was just waiting for them to say, and this is a whale pump, but it didn't come up. I think the thing is that in the future, we have to use our technology as much as we can, but we also have to utilize what's natural. And we have to understand that nature has been doing this for how many years? I mean, so it's something that we need to combine the natural and the technological to move further.
So human ways to mitigate. Solar panels. We have solar panels on roofs and big solar farms.
Yeah, my comments on some of these human ways to mitigate are really looking at, as a state, what we're not doing. We know that solar panels on rooftops are a very viable way to create your own energy or supplement energy. What we've seen at the legislative level from the majority party is really attempts to make it more difficult and more costly for people to have rooftop solar by limiting the amount of money that your utility company will pay you back. So if you create more energy through your solar panels than you use, you can sell that back to the utilities. Well, they're in the business of making money. The majority of the energy produced in our state is through investor-owned utility companies like Florida Power and Light that have a requirement to give money back to their shareholders. And so they've really monopolized the market on solar, and we continue to see bills sponsored at the legislative level that make it more difficult for for citizens to have rooftop solar. There's also things that happen with insurance, requiring exorbitant amount of insurance for rooftops if you put solar panels, and it just makes it more difficult for people to be more energy self-sufficient. We've seen in communities like Babcock Ranch, where they have solar, after storms are able to recover more quickly. And even in schools and places that are hurricane shelters, if they have solar panels and backup solar storage, they're able to provide some more continuity for the people who are using those systems and drastically reduce the bills for those school districts.
So we have wind energy. Is there much of this in Florida?
This is not something that's really a viable energy source in Florida right now, and the legislature last year took the step of banning it, and so preventing the opportunity to explore offshore wind production. So this is not something that we're going to be seeing in our state in the near future, and I see that as we're going to the next slide, looking at electric vehicles. I'll add that we had a preemption this year. Sarasota, other communities are looking at ways to put more electric vehicle charging stations. We know that Tesla and other companies are looking at superchargers. Well, the Department of Agriculture this year decided that they didn't like what was happening at the local level, and they wanted to be in charge of all of the solar infrastructure and deciding, or sorry, the EV charging infrastructure and being the ones to decide how and when that happens. And so any progress that's been made at local levels is likely to slow down because it now requires approval and oversight by the Department of Ag.
So this is a Chevy Blazer EV. It's actually our car. And this is a photo of the car on the campus here when we got to stay in the cottage. But I can tell you this is our second EV, and I would never go back to having a nice car.
Right.
Seawalls.
Thank you, thank you.
So seawalls, I would not put this in the category of mitigation for climate change,
Yes.
but there are ways that we can adapt our seawalls and look at things called living shorelines. And I don't remember if we have a slide in here. Seawalls, we're seeing that we're having failures of seawalls during hurricanes. There was an example from the city of St. Petersburg near the Vinoy Basin. But through programs like the Resilient Florida Grant Program, looking at ways to incentivize the creation of more natural shorelines, maybe not removing the existing seawalls, but putting natural features such as mangroves and oyster bars in front of that to help to dissipate some of that wave energy, but also create some of that natural habitat, store some of that carbon, and create some of those other ecosystem services. We also know that hardening beaches eventually can be detrimental. It also limits migration. So one of the slides that we saw earlier where you saw mangroves, salt marshes and mangroves, and as you start to creep more inward, there's a need as we see sea level rise and other changes associated with climate change for those habitats to be able to migrate upward. And if you have a protected slope of area, those natural areas, those mangroves will eventually start to move. But if you have a seawall or if you have a road or some other type of hardened infrastructure there, you really stop that progression and you'll eventually lose those habitats.
So what can government do? Well, we've heard from Lindsay a lot of things government can do. We can have representatives elected that can put bills in to help on a big level what can happen different from what we as individuals can do. But we as individuals, many of those ways to mitigate are things we can do. So we have to work together to do that. And as a result, this is what we want to get. This is called aspiring Gulf, right? It's an Eden version of what the world could be like. The water's all blue, the Gulf Stream just streams along isn't going to be challenged. We have giant oak trees and giant other trees everywhere that absorb the CO2 and create shade and places for animals. And we have a big sense of what we aspire to. So in the end, first I want to thank Dr. Hine, Robert Stackhouse, Lindsay Cross, because what happens is without all of us working together and expressing these ideas in very different ways is the only way we're going to be able to proceed. And we're only going to be able to proceed when we share information and educate ourselves and help to educate others. And I'll just end with this story about myself and in honor to former President Jimmy Carter. When I was in high school, he came and gave a talk from the White House. It was during the energy crisis. And he walked around the White House, he had a sweater on, and he went and he turned light switches off, and he talked about how to bring the temperature down in the White House and how to do that. Put your sweater on so it's cool. And he talked about recycling and things like that. Well, that talk by an important person about what we could do to help the environment is what has led me here and to make the art I make. From that time, I started recycling. I mean, I became the fanatic. I took every staple out of everything I had. But it was the President of the United States who basically talked to me very personally and sort of said, look, we have an issue here, and here's ways to mitigate it. He was a great supporter of solar energy. I had a friend who was a graduate student who graduated from Rutgers University. I grew up in New Jersey. And he started a solar company. I mean, and he was going great guns until Carter got out of office and all of that funding went away. But we need people who are visionary. People in government, Lindsay, can do a lot of things. And we're grateful to you for what you're doing. We're grateful to the scientists for what they do. And of course, we're grateful to the artists because they have the vision of everybody. And thank you to the museums, because museums are a vehicle. They're like great libraries. And without them, we wouldn't be able to see the history. And you've seen, it's not just contemporary artists who have thought about this. People throughout the ages, artists throughout the ages have done this. So I invite all of you to be the great innovators and mitigators that you are. And so thank you. And we can entertain a few questions.
Yeah, thank you.
Lindsay, in your efforts, trying to move us in sane ways as a state, it's so easy for the legislators to undermine those strategies and set us back. So we appreciate Lindsay Cross's efforts in trying to keep this legislature moving forward. It's an extremely difficult, frustrating process. Just from a citizenry level, being up there has got to be very challenging, and we appreciate you being there. Thank you all for your bringing this together in such a comprehensive and thoroughly presented artistic touch.
Many other ways to mitigate, obviously, we just touched on a few here. Geothermal is huge. In New Hampshire, for instance, I went to a college where they're spending $500 million right now to go completely off the grid, and they're using geothermal, they're pumping water down, and they're going to heat up and comes up, and that's how they warm the dorms, warm the classrooms, and obviously they use solar panels as well. looking into hydrogen, looking into small nuclear plants. And so the climate change is a huge economic opportunity. It shouldn't be viewed as killing jobs. And I give a lot of public talks about this sort of thing. When you have a problem, you stop digging. And literally you stop digging. And one of the things we can do right now is to stop using coal. Coal is just a filthy hydrocarbon. And it's got arsenic, it's got lead, it's got multiple other things. Acid mine drainage has such an acidity so low it can dissolve nails. It pollutes the air. So there's so many things that can be done. You can say, what could I focus on? It's just so widespread. Well, I focus on trying to kill off, as a geologist, which is probably sacrilegious, trying to kill off coal mining. Well, on the other hand, what do you do with coal miners? You have to do something with that. So we have to come up with some sort of societal mechanism to mitigate their problem. You can't stop coal mining and tell the coal miners to go starve or do something. They have to be transitioned. So the whole process of transition is going to be multi-decadal, if not century scale, to get off hydrocarbons and to get into a plethora of many other different types of energy sources.
We experience the hurricanes. We've got trends of CO2 that are trending towards renewable sources. Are we going to make it?
That's a great question, and nobody knows, right? I mean, I think that's one of the issues now.
But don't we know? Do we know? I mean, there's a scientist on the panel. I mean, what are the...
No, I think we will make it. I think it's going to be painful, it's going to be difficult. The first thing is education. We don't fully understand the problem as scientists, number one. And as a result of that, people don't understand science and the fact that, well, if you don't understand it, maybe climate change isn't real. So that's one of the things that kind of drives me nuts right now, is trying to convince people that science, that climate change is actually real. But it's like going to a doctor. We all go to doctors to get help. But on the other hand, if you ask the doctor about how well we understand the human body, he'll say, or she'll say, that we're just beginning. We're in the Stone Age as far as how the brain works. We're in the Stone Age as far as understanding how climate works. So it's enormously complicated, but we know something. We know something that can deal with cancer. We know something that can deal with various maladies in the human body. We know something about climate, so we can do something about it. In the process, we have to continue to learn more. So the investment in scientific research is absolutely critically important, and this foolishness about denying science. Climate change is absolutely ridiculous. It's like anti-vaxxers. It's just absolutely ridiculous. Of course we don't fully understand how vaccines work. But what we've understood in the past 50 years is absolutely enormous. Science is working at an exponential scale. We're just beginning. Modern science began maybe 100 years ago. As a species, we've been around for 300,000 years. For 300,000 years to 1850, we basically didn't do much science. Now, modern science is a result of AI, the result of quantum computing. Quantum computing is going to be absolutely spectacular. It's going to be hundreds of thousands of times more powerful than the most powerful computer right now. So we can take quadrillions of data points and generate models that we never could model before and make predictions in the future that we couldn't possibly make that would be much more accurate. So I have a lot of confidence in the capability of the science to be able to provide the solutions. The trouble is we have to have an educated populace that accepts the science. So I go back to third graders. I think we need to make third graders understand science better and accept science, and don't be afraid of science, don't be afraid of math. People avoid it because, oh, they're afraid it's hard, it's difficult. It's not. It's just the way we're teaching it is not the way we should be teaching it. Science is fascinating, and it should be made fascinating to 3-year-olds. So by the time that they get to be 23, they understand science, accept it, and be able to promote it to a much greater degree. And as better the science gets, the better the application and the technology gets, and we can ultimately come up with solutions.
One of the reasons I say we don't know is I think this is something that all of us share, is that having gone through this season with the hurricane season, and I think we're all in the sense of, well, what's going to happen next season? We just don't know. Is it going to be the same? Was it unusual this past season? Is it the norm? Is it going to be worse? And for us, if it's worse, we're all in trouble. but we don't know. We don't know if it's going to be worse or it's going to be okay. So in a sense, we're all living here in a sense of unknown, which is hard to do. But I think in some ways, that's where we are. Science is something that we can look to and will have solutions, but that takes a long time.
I think something that gave me a little bit of hope is a couple of years ago, Carol and I were part of a PBS 8-part series where they came to our studio and had us talk about climate change and used a lot of what you saw here to illustrate some of the points. And I believe it's still running. They're just very small little vignettes on PBS that run late at night, I hear. But anyway, the people that were doing it were young. They were young and maybe even younger than we thought, but they were dead serious about climate control. They're worried about their future, the world that they're going to inherit. And I think the young people are taking more interest and responsibility in this, of course, blaming us for all this too. So, but I think it's important to think of the youth as Al was saying, is that the younger the people are, the more informed they get and the more time they have to work on it.
It is interesting. These people that made the PBS, these young people, they blamed us. And they said to us, "You're really different. We didn't think people like you," meaning old people, even thought about this. I mean, they hold us responsible for the plight they're in now. And that really gave us pause. So I think we should stop here. And thank you for coming out to join us. I mean, that's so kind of you. And we're thankful of you. And it's always a pleasure to be able to talk about this and to talk about it with people who are like-minded. So, thank you.
Thank you very much.